Who's that boy? Who's that boy? It's Evan. Last day of new lecture. There's not even that much to cover because I'm that good of a lecturer. Probably not. I'm probably terrible online. Sorry about that, you guys. I wish I weren't here in my room recording, but that's what it is. I hope you're all keeping up good, just healthy and whatnot, both physically and mentally. We have integration by parts. This is just really extra practice. We're going to cover the first piece that I forgot to put in the video. So we'll cover this identity I forgot to put in the video. Identity. Put in Wednesday's video. But it was in the, hopefully it was in the, it was in the PDF, and hopefully you guys found it because you needed it briefly on the very last homework problem. But this is the identity. So I wrote this down. The integral of the natural log dx is x natural log x minus x plus c. So it's like, where does this come from? Or I'll ask why. Right? You guys love it when I ask why. That was all your test was, and I'm sure you guys just adored that exam. So let's answer the question why. Well, we know how to answer it. It's integration by parts. And if we follow our priorities, well, let's just go through it. So step 1 in integration by parts is identify u and v. So u, if we follow our priorities, should be the natural log. And I say v, or dv, I said, should be everything else. So what's sitting around then? dx. And then step 2, find du. This is 1 over x dx. And v is the integral dx, and that's just x. And so now you have step 3 is uv minus integral v du. That gives us x, natural log of x, minus the integral vx du, 1 over x dx. This happens to be x ln of x minus the integral dx, which is just x ln x minus x plus c. Voila. So you could have actually done this without having to view it in the PDF, because I did give you the answer with the priorities. It's definitely something you are able to accomplish, but maybe I wasn't as clear as I should have been. Anyway, this is something I really wanted to cover. It's a pretty cool identity, and I always like to, in the past I've put it on exams. I don't know if I will this time because I'm saying this, but it's a nice identity. Should just keep in mind. One of the best ones, I think. So that's what you get. That's a good one to keep in mind. It's really truly the integral of the natural log function, and that's why it's a good one. And you need integration by parts to find that out. Yeah, let's just do some problems then. So the first problem I want to cover is, I laugh at myself because I can't stress these things enough when I teach you guys, and you still seem to always forget that I say these things. So let's find the integral of the natural log of x e to the x squared dx. And hopefully by now you're catching on that I'm screaming at the screen, simplify what's inside. Okay, a lot of people write integrals that need to be simplified. And I mean, they look simplified. They are simplified to a certain extent, but they're not in the form that we want to see them in. it can be easier. Because what happens if I use my log rules, multiplication inside the log is the same as addition outside the log. So this is natural log of x plus natural log e to the x squared. And what's going on here is the natural log and the e cancel. So this is the integral natural log of x plus the plus x squared dx. That's all it is. Because the natural log and e to the x cancel. And we have, this is just what we talked about above. We know the integral there, this is the power rule. And you can see how much easier our life got by just simplifying what's inside. We have the one that's directly from above, bam, there it is, and the other one's the power rule. So this is exactly x ln x minus x, that's the first piece, plus the power rule piece, x cubed over 3 plus c. So just, if you see a problem that looks way too difficult, odds are it's not too difficult because it needs to be simplified. But I can't always give you the problem in its most simple form or the easiest form to integrate, because that's not how math is done. Nature doesn't necessarily give us everything in the easiest form. We have to put some effort in. So that's a good example. Another good example. This is an applied example. Oil production. Ooh. So oil production example. It says the estimated rate at which oil will be produced from a certain oil well T years after production has begun is given by rate of oil production given by R of T equals 100 T e to the negative 0.1 T. Now this is important. This is the rate, right? So this is a derivative. Can't stress that enough either, is rate and derivative mean the same thing. So the derivative of oil production is given by R of T equals 100 T e to the minus 0.1 T. It says find an expression that describes the total production of oil at the end of year T. Okay. So the total production at the end of year T, if that was the rate of production, if RT is the rate or the derivative, then the expression for the total production is going to be the antiderivative. I'll just circle this in green. Antiderivative. Because if we already have a derivative, all we want to do is get rid of that. So I'm going to say total production P of T equals integral R of T dt equals the integral 100 T e to the minus 0.1 T dt. And of course, this is an integration by parts problem. I'm going to pull the 100 out and just save myself a little bit of effort. We just follow our priorities. So integration by parts. So step 1, identify u and v. We follow our priorities on u. It's either a natural log or it's a polynomial. It's not going to be e, so this is going to be t, which makes dv e to the negative 0.1 t dt, everything else inside the integral. Step 2, we find du, it's going to be dt, and we find v, which is the integral of dv. And now we're gonna use that expression that I had given you guys before. I'm gonna write it down right here. It's e to the negative 0.1 t over negative 0.1. And I'll rewrite this down here. Comes from, we have this identity, and I wrote it on your exam too, you guys noticed. The integral e to the ax dx is 1 over a e to the ax. That's how you want to remember. That's a really important formula to remember. It comes from u substitution as well. So if you want to remember it as u substitution, go right ahead. This is alternatively negative 10 e to the negative 0.1 t. Anyway, so just keep that in mind. It comes from u substitution. Go ahead and use the u substitution if you want. It just saves yourself so much time to use that expression instead. And that's why I put it on your exam. Step 3, uv minus integral v du, which in this case is going to be negative. There was a 100 out front that I'm going to leave off for now, but I'll include it at the end. So in this case, it's negative 10 t e to the negative 0.1 t minus integral v du. So du is just dt, and v is now negative 10, so this is actually plus 10. Integral e to the minus 0.1 t dt, and lo and behold, this thing is going to help us a lot. We're going to use it again, and that's why I wanted to stress it. So part number 4 here is to actually evaluate. So this is negative 10 t e to the negative 0.1 t plus 10 e to the negative 0.1 t over negative 0.1 plus c. And so we can simplify that. Man, I'm not good at this today. We can simplify that as negative 10 t e to the negative 0.1 t minus 100 e to the negative 0.1 t plus c. And you'll remember there was a 100 out front, so pt equals, I don't know why I have an extra negative sign here. Negative. I don't know, that's fine. PT is 1000 t e to the negative 0.1 t plus 10,000 e to the negative 0.1 t plus c. We're going to have to determine what c is later. Yeah, these are negative. That's right. So these are negative. We have to determine what c is. Right. So since p of 0 is 0, should be production start, at 0 oil barrels, then we find P0 equals 0 minus 10,000 plus C, so C equals 10,000. That gives our expression for PT as 10,000 minus 1,000 T e to the 0.1 T minus 10,000 e to the negative 0.1 T. So this is like one of those initial value problems again. That's kind of all we ever have as word problems is initial value problems. For integrals anyway. So we have an initial value problem that required integration by parts. And we were able to use that. This nice thing in green, I like to refer to it quite often because we use it all the time. So definitely recall this thing in green because we're going to use it over and over and over again. So don't forget that. That's all I have. This is your last homework assignment, so rejoice. I'll see you guys all on Monday with reviewing for the final. Bye.